Alright, hey everyone, welcome back to my channel. So we'll be solving question 4 and 5 of this paper. So let's get started. So question 4. This question is about reactions of bases and acids. Ammonia is a gas at room temperature, and what is the test for ammonia gas? Describe the positive result of this test. Now, if you go to your syllabus, you're going to find the test for gases, and you'll know that ammonia turns damp red litmus paper blue. Of course, you're supposed to be memorizing these, so the more past papers you do, the easier it is for you guys to remember them. And of course, if you were given the chance to perform these experiments in person, that will definitely help you remember them even more. If not, there's a lot of videos online for you to check out. So let's place the test. So we got here damp red litmus paper. And as a result, it turns blue. Okay, so when it turns blue, that's when you know ammonia gas is present. Okay, so for part B, ammonia reacts with water to form ions. And this is the equation that we're given. So how does this equation show that ammonia behaves as a base? Now, it behaves as a base because it accepted a proton. You know, you have acids and bases. Acids donate protons. Now, here we're looking at hydrogen. It went from NH3 to NH4 plus, and H2O went to OH minus. It lost the hydrogen. Now, when we talk about hydrogen ion, okay, look, so we have hydrogen. It has an atomic mass of 1. It has a nucleon number of 1. So it only has a proton. So we got our proton right here. Actually, let's just do it in different colors. We got the proton, and then we got the 1 electron surrounding it. Okay, that's hydrogen. But when we have H plus, that means we lost that electron. It's positive charge now. It's a positive 1 charge. So then that disappears, and we're left with a proton. Hence why H plus is seen as a proton. But yeah, so how do we know that it's a base? Well, like we said, it's a proton acceptor. Now, aqueous ammonia is described as a weak base, so we need to suggest the pH of it. pH we know ranges between 1 to 14, with 7 being in the middle. And then when you're closer to 1, the more acidic. Closer to 14, the more basic. So it's a weak base, so it can't be 14. It has to be somewhere between 7 and 11. So that's the weak range base. So you can choose, for example, pH 8, and you'll get the 1 mark for it. Okay. Describe what is seen when aqueous ammonia is added to aqueous copper 2 sulfate until no further change is seen. Now, this is a test for aqueous cations. So cations have a positive charge. They're positive charged ions. All right, so if we check here, this is again in your syllabus, and with more practice, you'll get used to it. So we have copper 2 here, but we're mixing it with aqueous ammonia and not sodium hydroxide. So we have copper 2 sulfate, and we're mixing it with aqueous ammonia. So what's going to happen is you're going to get a light blue precipitate. When you keep adding more, it's soluble. So what happens is that you end up with a dark blue solution. So those are 3 points that you mentioned that will give you the 3 marks. So, okay. So aqueous sodium hydroxide, NaOH, is a strong alkali. In other words, it's a strong base. It reacts with dilute sulfuric acid. So we have NaOH, sulfuric acid, exothermically. What type of reaction is this? So it's an acid-base reaction. In other words, it's a neutralization reaction because it's opposites, and when opposites react together, it neutralizes it. It's kind of like when you have 1 proton and 1 electron, the overall charge is 0 because 1 plus negative 1 is 0. Okay. When we're dealing with neutralization, there's always going to be water. That is, generally speaking, that is one of the products. So what's left is NaSO4, but there's going to be a 2 right here. Why is that? It's because this polyatomic ion has an overall charge of 2-. And we know that hydrogen is, or the hydrogen ion is H+, and we do crisscross method like we mentioned in the previous video. The 2 goes here, the 1 goes here, but we never show the 1. So we know that sodium is in group 1, so it has a positive 1 charge. Its ion has a positive 1 charge. Okay, so let's balance this out. We have 2 sodium right there on the left-hand side, 2 on the right-hand side. We have 4 oxygens plus 2, so that's 6 oxygens. We have 2 hydrogens here and 2 more, so 4 hydrogens. So all we have to do is add a 2 right here, so we end up with 4 hydrogens, 2 oxygens on this side plus 4, which will give us 6, and now it's completely balanced. Okay, so part D. A student wanted to find the concentration of some dilute sulfuric acid by titration. Okay, the student found that 25 centimeters cubed of 0.0400 moles per decimeter cubed NaOH aqueous react exactly with 20 centimeter cubed of sulfuric acid. So name a suitable indicator to use in this titration. So a suitable one would be methyl orange. So you should remember that it's best used for titrations that involve finding the concentration of acids. Now, we need to calculate the concentration of H2SO4 in moles per decimeter cubed using the following steps. Calculate the number of moles of sodium hydroxide in 25 centimeter cubed. Okay, so let's do that. We know the general formula for concentration is C is equal to N over V. N is the number of moles, V is volume. So if you want to find number of moles, it will be concentration times volume. So you can remember it through this triangle. N is here, C is here, V is here. So C times V, and then on the top here is division. Okay. So N is equal to C times V. We have the concentration, which is up here, 0.0400 moles per decimeter cubed times the volume. The volume we have to change from centimeter cubed to decimeter cubed. So 1,000 centimeter cubed is equal to 1 decimeter cubed. So we'll keep that in mind. So we have 25.0 centimeters cubed times 1,000 centimeter cubed, and here we have 1 decimeter cubed. So what this basically means is that 1 decimeter cubed gives you 1,000 centimeter cubed. And the reason why I place centimeter cubed at the bottom is because I want to cancel these out and get rid of them, right? I also want to get rid of decimeter cubed, because when it's on the top, you can get rid of it. It's kind of like 2 over 2 is equal to 1. It just cancels out. I don't know, 40 over 40, it still equals to 1. So it's the same with the units. So generally speaking, you don't even have to write this part right here. You can just go automatically 25 over 1,000. But I wanted to add that and explain it to you guys. So then all we're left with is mole, which is what we need. And if you place that in your calculator, you'll get around 0.00100 mole. Always include the units, okay? Because they can take off marks when you forget to add a unit. Now, deduce the number of moles of H2SO4 that reacted with the 25 centimeter cubed of NaOH. So how you can do that is if you go back to when you go back to the equation, you'll see it's a 2-to-1 ratio. So for every 2 NaOH molecule present, there is 1 of H2SO4. So I'm going to place that 2-to-1 ratio. So that means if we have 0.001 moles of NaOH, we'll have half of that for H2SO4. So place that in your calculator and get 0.0000500 moles. Now I want to calculate the concentration of it in moles per decimeter cubed. Again, the formula C is equal to N over V. We have the number of moles, which is 0.0005 moles times, okay, we want decimeter cubed, so let's do this again. They used 20, so 1 over 20 centimeter cubed. Why did I do 1 over 20? Because it's the same thing. It'll still give me 0.005 over 20. It's still the same thing because 0.005 times 1 is still 0.005. Okay, so we have the centimeter cubed, we have moles. We want decimeter cubed at the bottom. So what we're going to do is put centimeter cubed at the top. So 1,000 centimeters cubed gives me 1 decimeter cubed. And that's when we flipped it. Like before I said that you can always flip it around. So centimeter cubed, centimeter cubed are gone. All we're left is mole and decimeter cubed. So what we're going to do now is place it in our calculator. We can clean it up for sure. It can be 0.0005 times 1,000 over 20, which will give us 0.025 moles per decimeter cubed. Now, calculate the concentration of this 0.04 moles per decimeter cubed NaOH in grams per decimeter cubed. Okay, so sodium has a mass of 23, oxygen 16, hydrogen 1, which gives us a total of 40. So that means there's 40 grams in 1 mole. Does that make sense? So 1 mole of NaOH has a mass of 40 grams. Okay, so now we have grams up here, but we have moles. We want decimeter cubed at the bottom. So what we do is this. We multiply by the concentration. So 0.0400 moles over decimeter cubed, which is perfect because then mole gets canceled out and we're left with grams per decimeter cubed. Place that in our calculator and we'll end up with 1.6 grams per decimeter cubed. And now we move on to the final question. So ethanol is manufactured by 2 different processes. So for each process, name the organic reactant and state the type of reactions. So one of the organic reactants is sugars. Sugars will help us manufacture ethanol, and the type of reaction is fermentation. There are also some videos online that you guys can watch if you're interested in seeing all the details. Another organic reactant is ethene, which is an alkene. That means it has a double bond, and it looks like that. The type of reaction is hydration. Hydration, you can think of water, well, to hydrate. So we're adding water to it, and what happens is it breaks that double bond, and we end up with ethanol. So we have one of the hydrogens goes to one of the carbons, and then the OH goes to the other carbon. It can be this carbon here, or it can be this carbon, it does not matter. Okay. Now let's move on. Alcohols can be oxidized to form carboxylic acid. Name a suitable oxidizing agent for this reaction. So one of them is potassium manganate 7. Okay, so next question. Alcohols can be partially oxidized to form aldehydes. Aldehydes are a homologous series of organic compounds. Okay, so alcohols can be oxidized, gives us aldehydes. All right. Partial oxidation is achieved by reacting an alcohol with the oxidizing agent in distillation apparatus as shown. Name apparatus A. So this is the Liebig condenser. If you don't remember the name, the Liebig is completely fine as long as you place condenser, and you're going to get that 1 mark. Now on the diagram, use 1 arrow to show where water enters the apparatus. It's going to enter from the bottom. And the reason why it enters from the bottom is that if it entered from the top, it won't fill up fully. It's just going to drain. But when you fill it from the bottom, it has to fill up completely before it exits. Okay, so let's move on. The table shows some information about aldehydes. Complete the table. So there's a pattern. You have ethanol, propanol, butanol. Here you have 1 carbon, so that is methanol. You should have memorized the prefixes by now. If you haven't, that's okay. Keep a sheet with you and keep using it until you fully memorize them. Now, for butanol, Okay, so here's the pattern. You have 1 carbon, 2 hydrogens, 2 carbons, 4 hydrogens, 3 carbons, 6 hydrogens. You can see that it's double. So butanol means there's 4 carbons, so that means double that will have 8 hydrogens, and oxygen has always been 1 in all of them, so it's just going to be an O. So let's deduce the general formula. It's going to be CN, and can be any number ranging between, well, 0 and, well, it's not going to be 0, but it's going to be 1 and up. Hydrogen is going to be double whatever that number is, so 2N, and then an O, with just nothing there because it's just 1. It's always going to be the same. Now, the structural formula of ethanol is shown. The C double bond O group is in aldehydes at the end of the carbon chain. Okay, this is a reactive part of the molecule. So what's the name that's given to reactive parts of any organic molecule? That name is the functional group, because it functions, it does stuff. Okay, so complete the dot and cross diagram to show the electron arrangement of a molecule of ethanol. Inner shells have been drawn out. Okay, so let's do this. Carbon is in group 4, so it has 4 valence electrons, so 4 electrons in its outer shell. We already know that hydrogen has 1 proton, 1 electron. Oxygen is in group 6, so 6 valence electrons. Okay, so let's start with the hydrogens. They're the easiest. So if carbon is given the dots, we'll give hydrogen the x's. So 1 dot from carbon and 1 x from the hydrogen. So that gives you that line that you see here. So for hydrogen, it only needs 2 electrons to fill the inner shell. And like we've mentioned before in the first video, you can check it out if you haven't. But if you want to find out how many electrons can fit in a shell, you use the formula 2n squared. Okay, so let's continue for the other hydrogens. There we go. Okay, now for carbon and carbon, when it's a single bond, it's just 1 electron from each atom. So you have 2 dots here. Now for carbon and oxygen, it's a double bond. So you're going to have 2 of each. 2 electrons from carbon and 2 from oxygen. But we're not done here. Oxygen has 6 valence electrons, and here we've only drawn 2, so there's still 4 more. But I'll place them a little bit further apart. There we go. So yeah, now we have a full octet for everything. If you want to double check, you'll see, let's use a different color. We have carbon has 8, so 1, 2, 3, 4, 5, 6, 7, 8. This carbon is all good. This oxygen has those 4, 5, 6, 7, 8. It's good to go. Hydrogen has 1, 2. Good to go. This carbon has 1, 2, 3, 4, 5, 6, 7, 8. It's good to go. So this is correct, and you'll be able to get all the answers, like all the marks. Okay, let's move on to the last part. So propanone belongs to a homologous series called ketones. Ketones end with -one. They have the same C double bond O group as aldehydes, but the C double bond O group is not at the end of the carbon chain. Propanone has the same molecular formula as propanol. What term is used to describe molecules with different structures but the same molecular formula? There's a hint. It involves the word structures, so that would be structural isomers. Now, it's just a structure. There's really not many ways you can draw this, but there's one way to draw it. So we have 3 carbons. We know that C double bond O will have to be not in the end, so that's just going to be in this one, right in the middle. It can't be in either ones on the corner. So we've placed the carbons, we've placed the oxygens. All we have to place now are the hydrogens, and we know that carbon can form 4 bonds because it has 4 valence electrons. So we have 1 here, we have another one here, 2, 3, there we go, we formed 4 total. 1, 2, 3, 4. We'll do the same here. And now if you count, there's 6 hydrogens, 3 carbons, and 1 oxygen. There you go, that's the drawing, and we're done this paper. So yeah, that's the end of this video. I hope you found it helpful. Share it with a friend if you think they'll need it. Subscribe for more, and let me know what questions you guys would like to see me solve next, and I'll see you all next time. Bye-bye.